We're going to start one of our final sections before the end of the year on water and solutions. And water and solutions will lead us into the study of acids and bases. If you remember, water is a bent molecule with a positive and negative end, and this gives water a polarity within the molecule, and we call water a polar molecule. The strong forces of attraction that hold water molecules to each other are called hydrogen bonding. Water can hydrogen bond with 4 other water molecules, making it one of the strongest hydrogen bonding substances there is. Surface tension is caused by these hydrogen bonds in water, creating a net downward pull. As they're attracted to each other in all directions except up, they create a net inward and downward pull, creating this surface tension on the surface of the water. Surface tension also pulls inwards in a drop. So you have the cohesive forces of attraction as the water is attracted to each other, the molecules, creating this drop formation. Water creates a meniscus in glass graduated cylinders because the water is attracted not only to itself with cohesive forces, but also to the glass with adhesive forces, as glass also can form hydrogen bonds with itself and with water. Solid water is an arrangement of a hexagonal structure based on the water molecule with its 105 approximate bond angle that stays constant as the water molecules attach to each other with strong hydrogen bonds. This forms our 6-sided snowflakes. In order to be water-soluble, your molecule must be polar, or water must be able to induce a polarity in the molecule. So these 2 molecules, the water on the left and the acetic acid on the right, would be soluble in each other because they both have polar structures. To be soluble in nonpolar solvents like the benzene on the left, a molecule must be nonpolar. So the trigonal planar molecule on the right would be water soluble in the benzene on the left, but it would not be water soluble. Would be soluble in benzene on the left, but would not be water soluble. This structure and solubility rule is often simplified as like dissolves like. Polar substances dissolve in polar solvents, and nonpolar will dissolve in nonpolar solvents. Here you can see a layering of 3 substances. Their densities place them at different heights in that test tube, but it's their intermolecular forces and differences in solubility that cause the layering. Oil and water don't mix because the oil, long straight chain nonpolar molecule, cannot interact with the polar water. And water is not able to induce a polarity in such a large molecule as oil. Water can hydrogen bond with itself, but also with many other substances. The methanol alcohol at the top left of this picture can also hydrogen bond, not only with itself, but with water. The hydrogen bonding takes place with the oxygen on the water molecule and the hydrogen on the alcohol molecule. Here's hydrogen bonding between water and ammonia. Soap has the ability to bring together substances that have different polarities. Soap itself has a large nonpolar or hydrophobic end and a smaller hydrophilic or polar end. The soap molecule will attach to the nonpolar substances with its hydrophobic end and with water on its hydrophilic end, and this allows the soap molecule to bring together oils and water and allow things that don't normally mix to mix and be washed away. Ionic solids are polar. They are attracted to the positive and negative ends of the water molecule and are able to be pulled apart by the water, which then surrounds the ions. The ions are then free to move throughout the solution, conducting an electrical current, and this is what defines an electrolyte. Gases are sometimes soluble. As the temperature increases, the solubility of a gas will decrease. So if the solution is cold, the gas will stay more soluble. The gas molecules are often polarities induced by water to keep them soluble. Many of our gases are nonpolar, such as oxygen and CO2, and they are not going to stay dissolved in water to a great extent, but water can induce a polarity and keep them somewhat dissolved. Chromatography is based on differences in polarity, which of course is a result of your intermolecular forces and your structure. So you did your chromatography lab and separated compounds. The separation is based on the differences not only in solubility, but in attraction to the mobile phase and the stationary phase. You can analyze and compare structures and identities of compounds through this method of chromatography. Solubility graphs are very common, and they let you know how much of a solid will dissolve in water at a particular temperature. So if you look at the pink-lined substance, you can see that it's not very temperature dependent. As you warm it up, not much more dissolves. But several of your other substances, solubility increases tremendously as you warm them up. And then the bottom line, the purple line, shows a decrease in solubility as you warm the substance up, which lets you know that this is probably a gas. Saturated, unsaturated, and supersaturated solutions can all be prepared in the laboratory. A saturated solution contains the maximum amount, so you dissolve until no more at that temperature will dissolve. Unsaturated could continue to dissolve more solute, and supersaturated is a particularly difficult solution to make. You have to create a solution that is literally holding more than it should be able to at that temperature, and then a small seed crystal or a little disruption will cause a large amount of solid to precipitate out. Making solutions will lead us into our acid-base chemistry. All acid-base chemistry is done in water solutions. Molarity is the unit of solution. It lets us know the concentration. It's a capital M, red molarity, and it's moles of solute over liters of solution. Moles of solute over liters of solution. You can make solutions approximately in a beaker, or you can make them very precisely in a volumetric flask. You will probably do both of these methods throughout the rest of the year. In order to calculate molarity, you simply need to be able to get the moles of the substance and the volume of the entire solution. So the molarity of a solution with 10 grams of HCl in 200 milliliters involves first turning the grams of HCl to moles by using the molar mass, and then dividing by the volume that has been converted into liters. Another problem that can be used with molarity, we want to know how many moles of nitric acid are required to make 100 milliliters of a 0.5 molar solution. This is a very common question that you'll have to answer when you make solutions in the lab. So first, I'm going to take the 100 milliliters of solution that I need to prepare, and using the conversion factor of the molarity, 0.5 molar, which means 0.5 moles in 1,000 milliliters, I convert the amount that I need to 0.05 moles. That's one method. Another method is to use the molarity equation itself, which would tell you moles is equivalent to molarity times volume in liters. Put the molarity in, put the volume in. You need to make sure you've converted it to liters, and moles will be your result. Either one of these methods is fine to use. How many grams of potassium hydroxide are needed or required to make 50 mL of a 0.1 molar solution? So the top method uses dimensional analysis. You need 50 milliliters of solution. The molarity of the solution you're trying to make is 0.1 molar, so that's 0.1 moles in a liter. Of course, a liter is 1,000 milliliters, so that conversion turns your value into moles, and then you use the molar mass to get to grams. If you use the formula method, you would say moles is equal to molarity times volume. You need to make sure again that your volume is in liters. That gives you a mole value, and then you still need to use the molar mass. 1 mole is 56 grams to get your mass or grams of potassium hydroxide. Again, either method is fine. How many grams of sodium chloride are required to make a 2-liter solution that's 0.1 molar? So once you work enough of these problems, you will say, for the top problem, I need to make 2 liters, so that's what I start with. The molarity that I want is 1 molar. So 1 mole in 1 liter is my next conversion factor for that problem at the top. And then I need to turn that to grams, so 1 mole is 58.5 grams of sodium chloride, and I get 117 grams of sodium chloride. Using the bottom method is molarity times volume in liters, and then times the molar mass. What's the molarity of a solution made by dissolving 20 grams of nitric acid in 800 milliliters? There's really only one way to do this. Take your 20 grams, turn it to moles with the molar mass of nitric acid, and then divide by the 800 milliliters, which you, of course, have converted to 0.8 liters. That gives you the molarity. How many milliliters of a 3 molar solution can be prepared from 5 grams of sodium chloride? Starting with the 5 grams of sodium chloride that you have, using the molar mass to convert it to moles, and then your final conversion is the molarity that you want to make. You want a 3 molar solution, so 3 moles, which would cancel with your moles of your molar mass, in either 1 liter or 1,000 milliliters, or your final conversion would give you 28.49 milliliters. Since we usually use a measurement of milliliters in the lab, 3 moles in 1,000 milliliters is probably the easiest conversion to do. There's another type of calculation, and this is one when you've already made a solution and you want to dilute it to something that's less concentrated. The equation for dilution problems is molarity initial times volume initial is equal to molarity final times volume final. Now, if you remember, molarity times volume in liters is moles. So when you dilute a solution, you don't change the number of moles. You change the concentration, but not the number of moles. So if you set the two sides of the equation equal, if the moles initial have to be equal to the moles final, then the molarity initial and volume initial will be equal to the molarity final and volume final, and you'll simply find the missing component. M1V1 equals M2V2 is the simplified version of the molarity dilution equation. So let's look at this problem. How many milliliters of 12 molar HCl will be needed to make 100 milliliters of 3 molar? So we have a 12 molar HCl solution. We need a 3 molar solution, and we only need 100 milliliters. So using M1V1 is M2V2 and plugging in the correct variables. So 12 molar is our M1. V1 is what we're looking for. We need to know what volume of 12 molar we're going to need so that when we dilute it to 100 milliliters, we will have made a 3 molar solution. So M2 and V2 are 3 molar and 100 milliliters. Solving algebraically gives us 25 milliliters. This means we need 25 milliliters of 12 molar that we will then dilute to 100 milliliters, and we will have made a 3 molar solution. How many milliliters of 6 molar HCl will we need to make a liter of 0.1 molar? So we're diluting our 6 molar to 0.1, and we want to make a liter of it. So M1V1 equals M2V2. So we take our original 6 molar. We're trying to solve for what volume of that we're going to need to use to make on the right-hand side 1 liter of a 0.1 molar solution. So again, doing the algebra, we're going to have 0.0167 liters. Liters is what the answer would come out in, since that was our volume V2 unit. Or, of course, we'd probably convert that to milliliters to measure out. So we need to pour out 16.67 milliliters of 6 molar HCl, dilute it up to a liter or 1,000 milliliters, and we will have made a 0.1 molar solution. What's the new molarity of a solution that's made by diluting 250 milliliters of a 0.5 molar HCl solution to 400 milliliters? Again, M1V1 is equal to M2V2. Take your original solution. You've got a 0.5 molar solution. You have 250 milliliters of it. You're diluting it on the right to 400 milliliters and solving for that new molarity. So your new molarity will be 0.31 molar. So by taking 250 milliliters of 0.5 molar and diluting it to a total volume of 400 milliliters, you will have made a 0.31 molar solution. What's the new molarity of a solution that's made by diluting 500 milliliters of 0.1 molar HCl to 800 milliliters? Again, 0.1 molar of a 500 milliliter solution is equivalent to, and you've got to solve for that unknown molarity. When you plug in your algebraic relationships, you get a new molarity of 0.0625 molar. So by taking your 500 milliliters of 0.1 and diluting it up to a total volume of 800, you've diluted your solution to 0.0625 molar. What volume of 12 molar HCl is needed to prepare 300 milliliters of a 2.5 molar? Again, now we're solving for the volume component. 12 molar HCl is what we have. We're solving for the volume. We're trying to make 2.5 molar solution, and we want 300 milliliters of it. So we're going to use 62.5 milliliters of the 12 molar, and we will end up, when we prepare the solution, to get 300 milliliters of a 2.5 molar. Hydrates are compounds that have water molecules bonded to them. These water molecules give the hydrate its color and its structure, its molecular geometry. Hydrates, the water is not the liquid water that you think of bonded in there, but when you heat the compounds, you will get the liquid water out. So this bonded water gives the crystal its geometry and color. Hydrate means bonded with water, and the anhydrate or anhydrous form is when you have removed the water. A hydrate formula has a dot in between the formulas, the compound formula on the left and the number of water molecules on the right. So this would be cobalt 2 chloride hexahydrate for 6 water molecules bonded to 1 formula unit of cobalt 2 chloride. When you lose the waters of hydration, hydrates will lose their color and they will lose their structure. When you add the water back, they will regain their color, not necessarily their structure, since you have destroyed that. You would have to regrow the crystal. But when they gain that water back, they release a tremendous amount of heat energy. That's steam coming off the surface of the compound that is rehydrated. The math for solving this is pretty simple. You have, if you're trying to identify the number of water molecules in a hydrate, you heat the compound. So you start with the mass of the hydrate. You then heat the compound until you've driven off all the water. You subtract the anhydrate from the hydrate. That gives you the mass of water. You then take the grams of the compound and turn it to moles with its molar mass, and the grams of the water and turn it to moles with its molar mass. Once you have the moles of the anhydrate and the water, you do what you have normally done with an empirical formula. You divide each by the smaller value, turning it into a whole number mole ratio, and getting the formula of the hydrate, barium chloride dihydrate. So finding the formula for a hydrated compound is pretty straightforward and simple. Okay? This will be all of the math that you've looked at in this podcast is pretty simple, and it will be the math for this chapter.